Here's some notes on waves, the concept of waves, doing a little bit of the math, even an example problem at the end here. Here's a couple of definitions. Waves are a disturbance or an oscillation, a repetition that travels through space, travels through time, and what they do is they transfer energy. That's what waves do. Even ocean waves, even though there is some motion of the water, there is essentially this energy that is being produced by the motion of the earth and the moon and everything around it that's causing these waves to crash on the shores. Of course, the depths of the oceans help that as well. Beginning of the year, we had this problem where there was trying to think about how you would measure the speed of a wave, right? The frequency and the wavelength. Here's above the shore shot of some different waves. You can see if you took a picture and you had this to scale, you could measure the wavelength. If you're sitting on the beach, even at night, you could time how often the waves crash up on the shore. You could get the frequency, okay? Again, waves transfer energy from one point to another. Usually the particles or what's the medium that the wave is going through does not move, is not being displaced. And so that mass really doesn't get moved too much. Of course, on the shores of the earth, of the oceans, there definitely is some motion and some movement in particles, but for the most part, it's generally not thought of as doing that. There are two different types of waves. First type is mechanical and physical. These are the ones we're going to be looking at today. And then there's also the electromagnetic waves, which we'll be looking at a little bit more next week. So the mechanical and the biggest difference between these is mechanical, physical waves. They have to have a medium to travel through. Okay? It could be a spring, could be a slinky, could be air, could be water, could be the earth. Right? They have to have mechanical waves have to have this medium or something to go through, to transfer through. Whereas electromagnetic waves, these really can go, in fact, they go fastest through no medium at all. Light and other electromagnetic waves actually go through space faster than they go through air. They actually slow down as they go through more dense mediums. Mechanical, physical waves, they actually go fastest through more dense mediums. Okay, what are the main two differences? We're going to look first mathematically at these mechanical waves today, this week, whereas next week we'll get into the electromagnetic. But they're pretty similar. They definitely have the same properties. Here's a couple different types of waves. There's a transverse wave. This is when the wave is moving, is oscillating perpendicular to the direction. So you can see the wave motion in blue here. This is the motion of the wave, the direction of the wave. But the slinky or the particles are actually moving in the perpendicular fashion or motion. Many different waves do this. When you talk about electromagnetic waves, they actually are transverse waves. They're two different perpendicular waves that are moving. One is the magnetic, that's why they're called electromagnetic. Usually electrical waves. In pink here, that's electrical field, and they actually move, so they're moving in this direction, perpendicular to that. And then the magnetic field is another third dimension to that wave. So that's how we think about electromagnetic. So they're a transverse wave, but it gets a little more complex in the thinking about that. Here's an example of a transverse wave with a slinky, and so the hand is moving back and forth, and so the motion, the particles of the metal are all moving in this direction, but the wave, as you can see, is moving in this perpendicular, this motion to the right direction, motion to the right, the direction to the right. You can see this transverse wave there. Another type of wave is a longitudinal, okay, and we think about this, it can be thought of vibrational or compression, and so you have this slinky where it would be moving from side to side, not up and down, but the wave is moving longitudinal direction to the, so it's moving along with the direction, the same way, back and forth. So you can see the slinky where it has compression, there's more dense, more closely compact parts of the slinky, and then there's rarefaction where it's stretched out. Okay, think about this in terms of sound or particles, or which sound kind of goes along with the last unit that we were looking about of pressure. It's really what sound is a pressure wave, vibrational motion through the air. You can see there's a example here with the actual motion of the slinky going back and forth and moving along the same direction as the wave. And so where it's compact, where it's compressed, that would be like a crest. And where it's stretched out, that would be like a trough. You can think about. Here would be some compression of air particles or wave. So it's the particles are getting closer together, bunched up, more dense, and then they're getting spread out. So you can think about this motion. This is how air sound waves work. That vibration in your throat gets transferred to the air, which transfers through the atmosphere, which goes into your ear, and you can actually pick up these pressure waves, these air pressure compression waves on the inside of your ear, right, in your eardrum. Pretty interesting. Sound waves definitely work in this fashion. Another couple types you can think about are surface waves, which can be compressional, they can be transverse, they can be longitudinal, but you can think about them in terms of going along the surface of something. And so here's a couple examples. This one on the right would be surface of a pond, and you throw a pebble in and it lands right where that plus sign is, and that wave gets spread along the surface of the pond. Or you can think about the ocean waves. This one on the right would be a transverse wave in all directions. This example on the left would be a transverse wave along the surface like the ocean, or from one side to the other. And so you can see these lines really aren't moving, but the energy is going through. Just kind of give you that example there. Now imagine this going through, how there being an earthquake, or some kind of disturbance, some kind of energy happening on the surface of the earth, where you have a seismic wave. You have something that can cause vast damage on the surface of the earth. You can imagine this being in the ocean, an earthquake along the ocean, or an earthquake on the surface where you have this major destruction. You have something causes cracks and motion and movement of the earth, and man-made things happening. Here's just I'm not sure if this is real or not, but this is something that has happened before, where cracks in the earth swallow things up, right? You don't want to. I've never experienced a major earthquake myself. It can be scary, scary things. Yeah, so seismic waves are waves that happen on the earth, and there's a couple different types of these. There's P waves, which are essentially compression or longitudinal waves along the surface. Just imagine what's happening on the surface there, a house or a car. You can have S waves, or kind of moving up, and that motion up and down, a transverse wave, right, causes great destruction. You can have this circular wave, and just imagine being on the surface here, what that would feel like, and something that's not very pleasant. It can be definitely scary. All waves have these properties, though. Think about these waves, whether they're longitudinal, whether they're transverse, seismic, along the surface. They all have these certain properties where they have some length between the waves. Okay, some wavelength. Wavelength means the length of one wave. Okay, you can measure that, and it's usually, and this is really a distance between these two disturbances. Okay, you can have a point where you have like a top, and we call that a crest, right? The top of the wave, where it's motion back and forth. You get this trough. Okay, and if you measure the height of this between this midpoint or this undisturbed state to the crest, you get the amplitude. Amplitude can also be measured from the center to the trough, or you can actually measure from the crest to the trough and divide that by 2 to give you the amplitude. Think about in terms of buying a stereo system, the amps, right? You can measure that. It would be in sound would be considered the volume of it. Okay, and this would be the direction of this wave, the motion, the energy going from one side to the other. Okay, this is what every property of every wave has to. If you measure the wavelength, it could be from the trough to the trough. It can be from the crest to the crest. It can be from this X here to this X here, wherever it repeats. Wherever it repeats. So going up to going up, right? That would be a repetition. Or here it would be going down to where it's going down. Here's at the trough to the trough. Wherever it repeats itself is the length of one wave. That wave is that disturbance from a repetition of this happening. Okay, some definitions here for you to deal with. We talk about frequency. We can time how long it takes a wave to move across from one place to another, how long it takes to repeat, how long it takes to oscillate. Okay, the frequency. Frequency is the number of waves that go by every second. And so we can think about number per second, the number of waves, right, that go by every 1 second in terms. And we call that's number per second, number per second is, we just designate that as hertz and abbreviate it capital H lowercase z. Per second, waves per second, oscillations per second, number of things per second. Okay, we can take the inverse of that. So this is measured frequency is per seconds, number per 1 second. The period is, well, let's flip that over and say, how long does it take for one wave to go by? What is the time per one wave? Okay, usually just measured in seconds. So hertz is a per second, period is the inverse of that is seconds. And so if you had a frequency of 3.8 waves are going by every second, yes, that would be the frequency. That would be equal to the inverse of the period. Okay, and so if we knew the frequency was 3.8 hertz, we know that's the frequency, then the period would be 1 divided by the frequency. That would be the frequency, and so period is the inverse of that. That would be period would be equal to 1 over the frequency. Frequency is 1 over the period. So do the math. Period is equal to 1 over the frequency. So you can plug that in and say 1 divided by 3.8. Let me clear this out. So it's not so confusing. If you did 1 divided by the 3.8, that would give you 0.26. Okay, so the frequency is 3.8. The period would be 0.26 seconds. That's how long it would take for one wave to go by. Okay, frequency is 3.8 waves per second. That means it takes 0.26 seconds for one wave to go by. Those are inverse of each other. Okay, the wavelength is is the length of